This is a video about running time. My name's Alan Doran. Before you watch the video, go and watch the video on binary search because we'll be using it as an example to compute running time. Make sure you've traced the algorithm through and you understand how it works. Running time refers to the time it takes a program to finish its job. It doesn't really have a technical meaning beyond that. What contributes to running time? Well, it depends on the input to the program. For instance, if you have a sorting program and you ask it to sort a very long list of numbers, it will take a lot longer to run than if you ask it to sort a very short list of numbers. So input determines the running time. Now, on top of that, you normally write your code in a high-level language, for instance, I don't know, Pascal or C++ or Java or something like that. And this is converted by the compiler into code that will actually be executed on your machine. The quality of the code that the compiler generates from what you have written determines the running time of the program. Some compilers actually have optimizers which vary the speed with which the program can run, often trade-off for debuggability. Now, the machine that you run the program on also has its own hardware which determines the speed with which it can execute the instructions that it's been asked to execute by your program. And that will determine the running time of the program too. So if you run a program on an old slow computer, it will take longer than if you run it on a new fast computer. Lastly, the time complexity of the algorithm determines how long a program that implements the algorithm will take to run. And this last point here is of considerable concern because it's a theoretical way of considering the speed of an algorithm irrespective of practical problems like how fast your computer is or whether or not your compiler was any good. So we'll actually be focusing in the next few slides on the time complexity of the algorithm. A simple model of computation for our purposes will do. For instance, a statement like read, print, return, an assignment, or a comparison between two values to see if one is less than, equal to, or greater than another, for instance, will each be assumed to have a running time of a single time step. A program then just consists of loops, modules of these statements, often arranged in sequences. So the running time of the program as a whole is just the sum of the running times of all of the executed statements. Now, of course, because we've got loops and modules, several statements might be executed multiple times. And in that case, each time they're run, we need to add one time step for that process. So a loop might iterate over a sequence 10 times, for instance, or 100 times, in which case every element of that loop or all of the statements in the loop will need to be executed 10 or 100 times. A module might be called several times, in which case the sequence of statements in the module will also be called multiple times, and each time they're called, they'll contribute to the running time of the program. Now, just to remind you briefly, binary search starts by looking at the middle entry in the list. If this is the goal, then we're finished. That is, if the thing we're looking for in the list is in the middle of the list, we don't need to search anymore. Otherwise, if the goal is less than the middle entry, for instance, if we're looking for a value in an ordered list that is, let me think, of alphabetically sorted names, and we're looking for the name Alan, then chances are it will be to the left of the middle entry. So we would have to look to the left half of the list to find Alan. Now we would do that by subdividing the list. That is, we're now interested in looking from the left-hand end of the list to the middle of the list, and we subdivide that again and we see to find if the middle entry in the left half of the list is Alan. Now, if it turned out that we had lots of A's in our list, or lots of names starting with A, then Alan may actually end up being in the right half of the list. So in that case, we'd be interested in looking from the middle of the list to the right hand end of the list, and we would subdivide that in two and look at its middle element, and so on and so on and so on, and we would continue to subdivide. If you didn't follow that very brief and probably not too clear explanation of the binary search, please go back again and watch the video on binary search. It's important that you understand how it works before you continue. Here is an alternative representation of the algorithm for the binary search. We've got two markers, one called lower and one called upper. And to start with, the lower marker is set to the first element in the list, and the upper marker is set to the size of the list minus 1. That is the final element in the list. Now, while the lower marker is less than or equal to the upper marker, we're going to iterate through this loop. And in the loop, we're going to be doing our search for the target element. Now, to begin with, we'll make the midpoint variable mid equal the lower plus the upper on 2. That is, we'll just set it to be the central element in the list. Now, you can see here have popped up a number of values in a column, one assignment, one comparison, and so on. These are just enumerating each of the statements in the algorithm that contributes to the running time according to our simple model that we saw on a previous slide. Now, in the loop, the first statement, let mid equal the middle value of the loop, is an assignment statement, and we're going to give it a value here of 1. Now, inside the loop, you can see there are a few more statements. There's an if, an else if, and an else. The if statement tests to see if the list's mid value, as just determined, is the target. If it is, we return. We've finished. If it's not, if the target is less than the middle value in the list, then we set the upper side of the list to be mid minus 1. That is, we're now going to focus our search on the location from the lower bound, which is unchanged from before. It's at the left-hand end of the list, if you want to think of it as sorted from left to right. And the upper bound on the list is now just to the left of the middle of the list. That is, we're now looking in the left half. If the target was greater than the list midpoint, then we would need to search on the right-hand side of the list. And that's why we move the lower bound of the list up to the middle point on the list plus 1. Now, we keep iterating through this loop until we've found the target. If we don't find the target, we will just return minus 1. That is, we'll exit the loop without having returned, and we'll reach the statement that says return minus 1. We'll return a negative value to say we didn't find the value that we were searching for. Now, the column one assignment, one comparison, and so on, has 10 elements in it. Each one of these contributes to the running time of the program. But more importantly, as we just saw, this loop in the middle will be iterated through multiple times. Therefore, all of the statements, 7 of them in the middle, will actually be iterated through multiple times and contribute more to the overall running time of the program than to the 3 values in the white bands. Now, as the number of elements in the list gets to be bigger, let's say it's 1,000,000, then we will be iterating through this loop so many times that the 3 values outside of the loop, that is one assignment at the top, and then the one return at the very bottom, these 3 things are almost irrelevant to the running time. And that's because we'll have to go through the loop so many times that the loop will itself dominate the running time of the program. Now, when we start considering things like this, we're not really talking anymore about the specific running time of the program, we're talking about its time complexity. That is, we're not really worried about little values like the 2 assignments at the top and the 1 return statement at the bottom. We're actually much more focused now on the loop. This is the dominant aspect of the program that will determine how long the algorithm that is implemented here takes to run. Now there are 7 things in that loop, but even if there was only one thing in that loop, still the dominant thing would be the loop itself, as the number of items in the list to be searched got bigger and bigger and bigger. Now how many times do we need to go through this loop? That's really going to determine the dominant aspect of the time complexity of the program. Well, it stops when we've found the target. Now in the best case and in the worst case, we'll have to go through the loops different amounts of times. So the best case scenario, that is for time complexity, is where we find the goal or the target immediately. We only need to execute the loop once in that case. That is, the program then would have constant time complexity. In the worst case, we don't even find the target in the list at all, and therefore we have to take our huge list, subdivide it in two, again, repeatedly subdividing the list into 2 until we've only got a single element left and we still haven't found the target. Then we return -1. So that's the worst case. Now in this case, because we're simplifying the problem each time by dividing the list in 2 and in 2 again, we've actually got a logarithmic time complexity. And in this case, we will have to loop at most log to the base 2 of the size of the list times. So binary search then has a best case time complexity that's constant. That's when the item is in the middle, and it's the first thing that we look at when we enter the blue loop on the previous slide. And a worst case time complexity that's logarithmic. That is when the item is not in the list at all. We have to subdivide the list into 2, again and again and again until we realise we're not going to find what we're looking for. Now different algorithms have different time complexities. So there are many different sorting algorithms, many different searching algorithms, many other programs too, of course, that implement different algorithms, and each of these will have its own time complexity. In general, the time complexity measures how long an algorithm takes for it to execute, and usually that's presented as a proportion of the number of input values, especially where there are many input values. So in the case of a search or a sort, for instance, the time complexity could be given as a proportion or as a function, if you like, of the number of values to sort through or search through. In summary then, running time depends on practical concerns, for instance, how fast the computer is, the quality of the compiler, and the size of the program's input. But it also depends on the design of the algorithm and its time complexity. Time complexity, being something that's not concerned with things like the speed of the computer, is therefore very important for us to understand, because even if we get a faster computer, if our algorithm is of poor time complexity, that faster computer may actually make very little difference. So one good reason for us to understand how to write algorithms effectively and efficiently. Thanks for watching.